Algebra 1, lesson 10.1. So we're in a new chapter, chapter 10, and chapter 10 is called Radical Functions and Geometry. Radical functions are functions where x is inside of a square root, technically any kind of root, a square root, a cubed root, a fourth root, etc., would be a radical function, but for this course, we're just dealing with square roots. So again, x is inside of a square root. We call that a radical function. And then the and geometry parts, we look a little bit at the Pythagorean theorem, and then we learn the trigonometric functions like sine, cosine, tangent. We don't do much with them. We just learn what the ratio is that's going on there. All right, so let's start to get some of this down. So this is lesson 10 point, sorry, issue of writing at the top of the page again, or at least toward the top of the page. 10.1, and we're calling this square root functions. Square root functions. And with this one, the textbook starts out with kind of getting us a little bit of a visual orientation of what's going on with square root functions. And so we have, I think for your homework, I think I have 4 of these for you to graph, and then to also analyze, okay, how is the function being changed compared to the parent function? And then what's the domain and range? And we'll get good notes for all of that, so hopefully you'll be really good to go. But square root functions are kind of the opposite of parabolas. They're kind of the opposite of quadratic equations. And opposite, more technically, I should say, they are the inverses. So let's start out with looking at the parent function of a quadratic function. So let's just see, quadratic, I'll say quadratic parent function. And the parent function for quadratic is y equals x squared. Okay? So when that's going on, if we made a little table of values, where this is x and this is y, and we say, all right, well, let's start maybe at -2. When x is -2, when you square a -2, you get +4. When x is -1, square that, so -1 times -1 gives you +1. 0, well, 0 squared is 0 times 0, which is just 0. And then 1 squared is 1, and 2 squared is 4. So when we connect all these together, we have our x-axis, our y-axis, and if we go 1, 2, 1, 2, 3, 4, 1, 2, we go out to 2, 4, or -2, 4, +2, 4, and then 1, 1, 1, 1, -1, 1, +1, 1, and 0, 0, and we connect them. Sorry, that was going to miss the mark. All right, let's see if I can do better here. Connect them, and we get our parabola. And part of what's happening is for every step you take x, you take a bigger step in y than the previous y step you did. So it's just like you're always going steeper and steeper and steeper and steeper and steeper each step you take. Okay? All right. Well, if we took this, what happens with inverses, and this is something that you'll learn more about later, but with the inverses, you start out switching x and y, and then you solve for the new y. So what I mean by that, so I'm going to say inverse. We would start out by saying x equals y squared, and we solve for the new y. Well, if we wanted to solve for y, what would we do? We would need to take the square root of both sides. So if I take the square root of both sides, what I would get is I would get y equals plus or minus the square root of x. We need that plus or minus because my y that I plug in here could be a positive number or a negative number. If y is +2 or if y is -2, I'll get the same answer for x, right? So if x is 4, what values of y can make that true? But a positive 2 or a negative 2, because if I square the negative 2, I get 4, just like if I square a positive 2, I get 4. So that's, again, why I need that plus or minus, okay? Oops, I didn't need to erase all of that. That's part of what I'm doing here. All right. Well, if we graph well, I'll tell you what. Let's do a table of values and kind of see what's going on. So let's do one for x, and then y when we have y equals the positive square root of x. And let's do another table of values here where we have x values and then what we get for y when y is the negative square root of x. So I'm going to intentionally pick x values here that have nice square roots. Okay? So I'm going to go with, well, how about negative 4? Oops, not negative 4. Sorry. 4 has a nice square root. So if x is 4, y is the square root of that, which is 2. How about if x is 1? The square root of 1 is 1. How about if x is 0? The square root of 0 is 0. Because square root, again, is what number times itself equals this. So the square root of 0 would be asking what number times itself equals 0. Well, 0 times itself equals 0. Okay. Let's do the same thing with these x values, but now if x is 4, the y value that we get is negative square root of 4, which is negative 2. And if x is 1, the y value is negative square root of 1, which is negative 1. And then 0, negative 0 is still 0. So if we graph these now, let's see what we get. Oops, I didn't label my axes over here or finish putting the arrowheads. Sorry. All right. X-axis, y-axis. So I have the point 0, 0. Okay. Then when x is 1, I have a y value of positive 1 and negative 1. Then when x is 4, 1, 2, 3, 4, I have a y value of positive 2 and negative 2. And if I connect these, guess what I get? I get a sideways parabola. And that's what happens kind of with inverses, that kind of flips things on a side. More technically, what it does is it takes, if you have this line y equals x, and you took that parabola and you pretended that that blue line is a mirror, and you flipped the parabola over that mirror, then what you would get is a sideways one that we're dealing with. Where we technically have two different equations. We have the positive, y equals the positive square root of x. That's the top half of this parabola, sideways parabola. And then we have y equals the negative square root of x, and that is the bottom half. But you put those two halves together, and what do you get? You get that whole sideways parabola. All right, so that's a little bit about what's going on. What we're dealing with here are these half sideways parabolas are the equations that we're dealing with, okay? And so I could say what this is this is parent function. This is a square root function again. Square root, and this is the parent function. Oops, I already wrote the word parent, now it's function. Function, and the parent function is technically, oops, not that one, wrong one, it's the positive one, is the y equals the positive square root of x. Okay? All right, but what happens with changes to these things? Well, let's look at that. So I'm going to write something like this. Y equals a times the square root of bx plus c. Nope, bx plus h is what I want. Plus h plus k. Slightly different from what your textbook has, but there are reasons why I'm going with something that is slightly different. All right. And let's look at what these changes do. Well, a is the vertical stretch or compress factor. You might recall that from last chapter where we were vertically stretching graphs or vertically compressing them. Okay? And so what we could say is if absolute value of A is greater than 1, then it's vertically stretched. So I could say stretched, ETCH, stretched vertically. And then if absolute value of A, I need to say is between 0 and 1. Absolute value of A. Oh no, absolute value of A is less than 1, which is the same thing as saying, i.e., 0 is less than A is less than 1. In other words, A is between 0 and 1. Wait, absolute value of A is less than 1. Well, or 0, negative 1 is less than negative A is less than 0. I shouldn't put that. Sorry about that. Then it is compressed vertically. Okay? And then one other thing I could say if A is negative, then it is vertically reflected. And we saw that up here with this red one. When we had y equals the negative square root of x, we got the bottom half of the parabola. Or in other words, it took the yellow one and it flipped it upside down to become the red one. Okay? All right, so we had that piece. And then I'm going to say this. The domain is this. We take bx plus h is greater than or equal to 0 and solve for x. Because here's what's going on. With our parabola, you can plug any x value into the equation and solve for y. Any x value you want, however big, however small, any x value you can plug into the equation and you can solve. And you can get an answer. Lines are the same way. Any line, unless it's a vertical line, any other line, you can plug an x value in and you can solve for what y is. Well, with these, we are limited in what x values we can plug in. The reason why is because what's inside of a square root cannot be a negative number unless you're willing to start dealing with imaginary numbers, and that's something that we're not getting into at this point. So unless you want to, unless you are willing to do, unless you're willing to deal with imaginary numbers, you have to make sure that what's inside the square root is 0 or bigger. And that's what we mean by this greater than or equal to 0, that it's 0 or bigger. And so that tells us what x values our graph will have. And then for what y values our graph will have, our range is y is greater than or equal to k if a is positive and we have y is less than or equal to k if a is negative. And the reason why, so if I scroll up here again, here for this yellow one, y equals the square root of x. So what's k? Well, technically we have a, Technically we have a plus 0 going on there. So k is 0. So what that tells me is that the range is all y values 0 or bigger. In other words, what y values does this yellow graph have? Does this yellow graph have? It has y values 0 and bigger. But then same thing, this red one, what's the k value? Well, technically plus 0, so the k value is 0. but we have a negative square root. Negative square root flips it upside down. So for the red one, we have y values 0 and below. Okay, so we have y values that are less than or equal to 0. Less than or equal to 0. All right? And this really kind of tells us all of the information that we know in order to graph these. So let's do a couple examples, and hopefully the different pieces will click. So what you do is you go with the general shape. Imagine you're doing the top half or bottom half of a sideways parabola. And really what we care about is that the shape is roughly correct and that it starts at the right place. So let's look at that. So let's say example. Here's what we want to do. We want to state the domain and range. That's part A. And B, identify how the function, technically these are, well, if you're dealing with only half of it, it is still a function. If you're dealing with both the top and bottom halves together, it's not a function because it fails the vertical line test. Right, identify how the function is related to y equals the square root of x. In other words, the parent function, and then C, graph. Okay, let's start out with this one. Let's start out with y equals the square root of x plus 3 plus 2. Okay, well, for the domain, here's what I know. I'm going to do blue because it's like my work. The domain, I know that x plus 3, what's inside the square root, we call that the radicand, is what's inside the square root. I know that what's inside the square root must be greater than or equal to 0. So I'm going to say x plus 3 must be greater than or equal to 0. And then I solve for x. So I need to subtract 3 from both sides. So what that gives me is x must be greater than or equal to negative 3. Okay, that's my domain. Then my range, well, I note that I have this k value of 2. That's that right there. Okay, a positive 2. And I also note that it's a positive, oops, wrong one, sorry. I also note that it is a positive square root, so it opens upward. So then what that tells me is my range is y is greater than or equal to 2. Okay. All right, so that's part A, the domain and the range. And really that gives me enough to sketch a graph at this point, but let's go ahead and do part B. So that was part A. Part B. All right, how is this related? Well, we don't have, we have an A value. The A value is technically a positive 1, right? So the A value is positive, so there's no reflection going on. The A value is 1, so there's no stretching or compressing. So we don't have any stretching, any compressing, any reflecting going on. All we have are translating, or translations. And notice the graph usually would start, like my parent functions here. My parent function starts here at 0, 0. All right, well, what has happened to the x value of where I'm starting? What has happened to my domain? My domain, instead of starting at 0, it is starting at negative 3. So what that tells me is I am translating, I'll say translated 3 units left. Because instead of starting at 0, the x value of 0 is starting at an x value of negative 3. And then we also are translated 2 units up. And I know 2 units up because instead of starting at a y value of 0, I'm starting at a y value of positive 2. So this positive 2 tells me it's gone up 2 units for the y values. And then the x value here of negative 3 tells me it is translated left 3 units. Okay, and we can do our graph. So let's do our graph. So I need my x-axis, my y-axis, and x-axis, y-axis. So my parent graph starts at 0, 0. This one starts at x value of negative 3, 1, 2, 3, and a y value of 2, 1, 2. So this one starts at negative 3, comma 2, and I do the top half shape like that. And that's my graph. Okay, let's do another one. This time, let's deal with, instead of y equals square root of that, let's do y equals negative 2 square root of 2x plus 3 minus 1. All right, we have a lot going on here. We'll just take it one step at a time. So first we need to find the domain. For finding the domain, what do? I take what's inside the square root, that is 2x plus 3, and I make it greater than or equal to 0, and now I solve for x. So I need to subtract 3 from both sides, but that is going to give me 2x is greater than or equal to negative 3. And then divide both sides by 2, so I get x is greater than or equal to negative 3 halves. That's my domain. Or in other words, my graph will start at an x value of negative 3 halves and then go to the right because those are bigger x values. All right, now let's look at the range. Well, up here, we said that the range is y is greater than k if a is positive, or y is less than or equal to k if a is negative. So here, I have a negative a value. It's negative 2. My a value is negative 2. And my k value is negative 1. Okay. So then my range is going to be y is less than or equal. I picked less than or equal because a is negative. But the number out in front of the square root is negative. So I'm with less than or equal to. In other words, I'm dealing with the upside down. I'm dealing with the bottom half. And the bottom half goes down, not up. So because it goes down, all of my y values are less than or equal to some value. And what value are they less than or equal to? They're less than or equal to negative 1. So that's my range. Or in other words, my graph will start at the point negative 3 halves, because that's x, comma, negative 1. And because this x is greater than, that means it'll open to the right. And because this y is less than, that means it'll open downward. All right, how is this changed? This is part B. Well, I can do my translations. It's translated left negative 3 halves units, which is negative 1.5. I went left because this, oh, sorry, it's not translated to left negative. It's translated to left 3 halves units. The left takes care of the negative because if you're moving to the left, you're moving in the negative x direction. So it's translated left 3 halves units, and it's translated down 1 unit. Down because it's a negative 1. What else do we know? Well, I have a negative here, so that is reflected. So it's vertically reflected. So we have, oops, blue pin. There we go. Vertically reflected. And then I have a 2 here. So what does that tell me? that tells me that it is vertically expanded by a factor of 2. And what does that mean? That means if our unchanged one is like this, if it's expanded, it'll be more like that. It's taller. It's kind of a way of looking at it. Okay? And that gives me all the information that I need for graphing this. I'll go ahead and splash the graph right over here. Axes, arrowheads, labels. So I'm starting at the point -1.5 comma -1. So I'm going to make my scale just a little bit bigger here. -1.5 comma -1. So I'm starting here. And I had a negative square root of -2 square root. So that means it opens downward. It's going to open downward and it's going to be stretched a little bit. So I'm going to make it just a little bit quote-unquote taller. And maybe we'll make it a teeny bit taller than that. What you could do is you could maybe find out where it crosses the x-axis. Or sorry, where it crosses the y-axis. It crosses the y-axis when x is 2. I'm sorry, crosses the y-axis when x is 0. That's going to be something kind of ugly, but we can approximate. Let's just see if we did y equals -2 square root of 2 times 0, I'm plugging 0 in for x, plus 3. That plus 3 is inside the square root. That's very important. Minus 1. And let's see what this approximately is. Well, that's the same thing as -2 square root of 3 minus 1. And we can just get a decimal here because the square root of 3 is a decimal. It goes on forever. So let's see roughly what we have here. Grab my calculator. We have the square root of 3. I'm going to go ahead and do that first. Okay, times a -2. I'm using a calculator I don't usually use here. Okay. And then I need to do -1. So this is approximately -4.46. So 1, 2, 3, 4, about 4.5 is where it crosses. So this needs to go more like that. Okay? You don't have to be super detailed like that. I mean, that's not even super detailed, but I found one more point. But, it could have been even a little bit easier. If you can find an x value that will give you a nice square root, if we had gone with x equals 1, that would give us -2 times, oh wait, not 1, 3, 4, 5, 6, 7, 8, 9. If we had gone with x is 3, that would give us 2 times 3 plus 3 minus 1. But this is going too far out. I went with that because I'm like, okay, what's an x value? Is there an x value that can give me a perfect square inside the square root? Because 2 times 3 is 6, plus 3 is 9. We know what the square root of 9 is exactly. That's 3, so -6, -7, so it's become -7. So when x is 1, no, when x is 1, 2, 3, we're down here at -7, which is not quite exactly as I drew it. Getting the general shape and generally making it a little bit taller is fine for our purposes. But there we go. So that's what you're doing for this lesson. You are identifying the domain and range, you are identifying how the graph is changed from the parent function, and you are sketching a graph. Okay, I hope that makes sense. Let me know if you have any questions. And again, this is just kind of giving a little bit of a visual of what's going on with these. And the big eye, the bird's eye picture, if I scroll back up to the top, is that with our quadratic functions here on the left, every change, as we keep taking steps in horizontal steps, steps in the x direction, our vertical steps get bigger and bigger and bigger. With these, it's the reverse. We have to, as we keep taking steps in the x direction, our vertical steps are getting smaller and smaller and smaller. And there are a wide variety of things in the real world that model or that have this kind of a relationship, especially when you get into like velocity versus distance kind of stuff, or when you have acceleration and the relationship between the two. Um, yeah. All right. Again, let me know if you have questions, and I hope it goes well. Thanks. Bye.